Right, before we get into these, and there is an independent event, so I'm just going to make that a touch smaller. What is probability? What is it? If I say to you the word probability, what do I mean? What am I referring to? You are welcome to unmute yourself if you want. Nice, Manuel. Okay, so probability is the chance or the likelihood of an event occurring. So what we need to bear in mind is that probability exists on a scale. So what I mean by that is it can range from 0 to 1. Now that's important to know, because if you get a probability value that is less than 0, or probability value that is greater than 1, you have done something wrong. It should exist somewhere between 0 and 1. 1 being a certainty, 0 being impossible. Okay, when we write our probabilities, there are 3 ways we can represent it, either as a fraction, as a decimal, oops, I'll fix it now, or as a percentage. We don't really care which one you choose to use. It is completely up to you. Most of the time you're going to be using a fraction, because that's what the probability rule, I say probability rule, that's how we work out probability anyways. So 90% of the time you're going to use a fraction. The only time I would suggest writing it as a decimal or as a fraction or as a percentage is if the question specifically says, determine the probability of this event as a percentage. Otherwise, just leave it as a fraction. That's it. You don't even have to simplify it. I'll chat about this in a second, but we don't really even care if you simplify or not. We should always simplify. I always simplify because mathematically, we must simplify, but it's not the end of the world. Okay, so that's what probability is. In this green block, so I'm just gonna, apparently I'm not going to scroll anyway. So in this green block over here, this is what we call the probability rule. And this is a rule that is given to you on your formula sheet. You get this, you do not need to learn it, it is there for you. The other piece of information you get with probability is the basic, how do you work out probability? So probability is determined by taking the number of outcomes in an event divided by the total number of outcomes in your sample space. Now your sample space, okay, I'm going to fix it now. Your sample space is all possible outcomes. So basically you take the number of favorable outcomes divided by the total number of outcomes. If you think of rolling a dice or a die, the number of odd values on a die is 3, 1, 3, and 5. So you've got 3 odd values out of a total 6 odd values. You would say 3 over 6. That is your probability formula, for lack of a better description. This probability formula, exactly as I've written it here, is also on your formula sheet. But those are the only 2 things that you are given with regards to probability. That's it. Okay, nothing else. So when it comes to independent events, you need to know the independent event rule, and we're going to get to that later. I'll write it down for you. When it comes to our other events, mutually exclusive, exhaustive, and complementary, they are like features that make those events what they are. You can learn them if you want to. It's up to you. Okay, I'm going to write them down for you. If you want them, they're there for you. If you don't want them, don't use them. Whatever floats your boat. Okay, so first things first is mutually exclusive events. Mutually exclusive events are events that have no outcomes in common with each other. So basically, there's no intersection. So you can see in these diagrams, these are called Venn diagrams. We should remember that from grade 11. In the Venn diagram for mutually exclusive, there is no overlap of my circles. There's no intersection. So there are no common outcomes between mutually exclusive events. Basically, what that means is the events cannot occur at the same time. So, oops. English has deserted me today at the same time. So, for example, if we go back to our rolling a dice situation, you cannot roll both an even and an odd number at the same time. That is not possible. A number is odd or even. That's it. Okay, so it is not possible for you to roll both at the same time. You're going to roll one or the other. Those would be mutually exclusive. Now, because there's no intersection, what that means is that the probability of A and B, so the probability of them occurring at the same time, is 0. So that is, if you now link that back to your probability rule, this last term over here, probability of A and B, that would be -0 because there is no intersection between your events. Exhaustive events are, we'll get there in a second, are events that together fill your sample space. So what that means is your outcome is going to be in one of your events. If you had 5 events, your outcomes are all going to be in one of those 5 events. You've got nothing left in the space around the events in the block. They fall into one of your circles. So the events together fill your sample space. Now remember, the block or the rectangle is your sample space. It contains all of your possible outcomes for your event or your experiment. For the sample space. Now what that means is because all of your outcomes are contained in one of your events, it means that the probability of getting A or B, so one of your events or even both of your events, is 1. Oh, it's going to get there eventually. So the probability of A or B is equal to 1. So A or B means I don't care if it's A, I don't care if it's B, I don't care if it's A and B at the same time. As long as it's one of them, you will have a probability of 1. And you can see this. If you go to a Venn diagram, I don't care if it's A, B, or both. I just want everything in A or B. That's all of the outcomes. So it would be 6 out of 6 outcomes, a probability of 1. Right, complementary events are then events that are both exhaustive and mutually exclusive. I hate writing mutually exclusive. It's such a stupid thing because there are so many longer things in math that we have to write down. The mutually exclusive just annoys me. Right, so not only is there no intersection between these events, your outcomes are either in A or B, C or D, whatever. It must fall in one of your events. Complementary events sort of leads us to a rule that's very helpful to us, whereby if you want the probability of one of your events, you just say 1 minus the probability of not that event. So if I wanted the probability of A, 1, because it is exhaustive, so all of your outcomes are contained in your sample space, minus the probability of B, because what's left is A, the probability of A. So when we are looking at, or when we are given information about not A or not B or something like that, if we want the probability of that event, we just say 1 minus. Make that a bit neater. Okay. Independent events, its name kind of gives it away, but basically the probability of one event is not influenced by whether or not the other event occurs. So what I mean by that is the probability of you getting 80% in maths is not affected by your shoe size. Those are independent events. Your shoe size has absolutely nothing to do with your maths mark. Independent. The result of one has no effect on the other. I'll try to write that concisely. Apparently, I'm not going to write that concisely. We try again. Now, this independent rule that I'm going to write down in a second, you have to know this. This is not on your formula sheet, and I can pretty much guarantee that you're going to be asked about independent events, so you need to know this rule. Right, so I'll write it down in a different color because it is important that we know this. So independent events, their rule is that the probability of A and B, so essentially the intersection, is equal to the product of those two events' probabilities. So the probability of A times the probability of B. So like I said, this is not on your formula sheet, but I can guarantee that you're going to be asked about independent events. Those of you that have already done probability or that were probably examined on probability in your exams now, there was probably an independent event question. Okay, it's going to come up. Learn the rule. This is the only rule you need to learn for probability. Like I say, you can learn these other characteristics of mutually exclusive, exhaustive, and complementary, but they sort of fall into place when you start doing your calculations anyways. What you need to learn, though, is the independent events rule. Okay, so you take nothing away. You take away independent event law or rule, whatever you want to call it. Right, so I'll wait here for a second in case you want to screenshot that little breakdown. But basically what we need to be able to do is we need to be able to use these bits of information or these characteristics of each of these events in order to answer some questions. So I can say to you, prove that they are mutually exclusive. So you would need to prove to me that the intersection is 0. I could say to you, are these events independent? You would need to prove that the probability of A and B is equal to the probability of A times the probability of B. I could tell you these two events are exhaustive, and then you can use that bit of information to answer some questions. So it's all going to depend on what I give you, but we can now use these bits of information and these characteristics to answer questions. I was thinking of something that I was going to say there, but obviously it's now out my head. No idea. I'm sure it'll come to me when we do questions. Right, so I'm going to assume you've got those screenshots. Let's make this a little bigger, just a smidge. Alrighty, so a 6-sided die is rolled. Die is a dice. Die is a singular. I'm sure you know this. Die is a singular. Dice is plural. So you've got many dice, one die. If you don't know that, now you do. Just if they're going to use a die, they're going to use that word. So just understand what it means. So a 6-sided die is rolled and the number on the landing face is noted. So however, if it lands with a 4, that is the landing face. Consider the following event. So before we even get to the questions, which I'm just going to get rid of for a second, let's consider what's happening here. So a number less than 3. Well, if you think of a dice or a die, the only numbers less than 3 are 1 and 2. Now, I like to write down my outcomes if I don't have them, just because I'm going to be asked the probability and it's going to be useful to know. Event B are your even numbers. So on a dice, that's 2, 4, and 6. And then event C is nice and easy. It's just the number 4. So the number 4, that's it. So those are the outcomes with which I'm working. We can see that we don't have all the outcomes for our dice here. So 3 and 5 are not included anywhere here, but that's okay. It doesn't matter. We've got this. Okay, so question A says, what is the sample space? Can anyone tell me what sample space is? We have already sort of discussed it, but what is the sample space? Nice, Angie. Okay, so Angie said the numbers 1 to 6. So a sample space of an event or an experiment are all possible outcomes. And obviously I've chosen the thickest pen to write in, but we're out here making it work. So it's all of your possible outcomes. Whenever you need to list your sample space or list the events or outcomes in an event, you use a symbol that's appropriate. So sample space is S, and then we use curly brackets. Guys, remember your curly brackets do not have to be perfect. If it's quite literally a curve, a little arrow and a curve, that's fine. Do your best. Okay, we're not marking you on your ability to draw a curly bracket. So it is exactly as Angie said, 1, 2, 3, all the way up to 6. And your sample space is useful for you because, again, if you need to go and determine probabilities, you need to know what outcomes make up your sample space and how many there are. Now we've been asked to determine probabilities in question B, and we want the probability of A, B, and C. Cool. So probability of A is the number of outcomes in event A, so that's 1 and 2, so 2 outcomes, divided by the total number of outcomes, which is 6, 1 over 3. Like I said, I always simplify. You're not marked down if you don't simplify, but my advice is simplify. Okay, this pen is very aggressively thick, and I don't think we need to be so in our faces. Right, the probability of B, there are 3 outcomes, 2, 4, and 6 are even numbers out of a total possible 6. So the probability of event B occurring is 1/2. And the probability of event C occurring, it's only 1 outcome out of the total possible 6. So 1 out of 6. I'm just going to rewrite. Okay. I'm not going to rewrite. So when working with probabilities, that's it. Number of favorable outcomes divided by the total. So question C says determine the probability of not A. So just so that we're all aware, this little dash or apostrophe means not. So we're talking about the probability of not A. Now, guys, there's a couple different ways that you can do this. Obviously, the first one is to say 1 minus A, because remember we said that the probability of A is equal to 1 minus the probability of not A, which if you then shuffle that around, that therefore means that the probability of not A is equal to 1 minus the probability of A. So if you want to use that rule, that's absolutely fine. I'm going to show you how to do it with that as well. That some people are visual learners, visual academics. And so a Venn diagram might actually be helpful in this situation. I'm going to draw the Venn diagram. You need to decide what works for you at the end of the day. All right, so we've got 3 events, A, B, and C. So that means we need 3 circles. Beautiful circles. And we need our sample space. Shame. Okay. No, it really doesn't like me. Wait. Okay. Right, we have 3 events, like I say, A, B, and C. You label your circles appropriately. I don't really care what order you choose to label them in. I'm just going to go clockwise. A, remember, was, I'm scrolling so aggressively, was numbers less than 3, so that was 1 and 2. But remember, 2 fell in event B as well, so there's an overlap between A and B. So 2. 4 is the overlap between B and C, so there's just 6 there, and that's it. And then obviously we've got the 3 and the 5 outside. We have them outside somewhere. Right, there we go. So you can use a Venn diagram. Again, guys, I don't care. You do you. So for some people, the rule is probably the easiest. Personally, I would just use the rule. So if I want the probability of not A, so A dash, you can write not A if you want. Again, really makes no difference. It means the same thing. We would just say 1 minus the probability of A, which is 1 minus, we've just worked out the probability of A to be 1/3. So 2/3. That's it. Okay. If you were to use your Venn diagram, the probability of not A is saying, I want everything that is outside of A. So we need to ignore everything in A's circle, including the 2, because that is still part of A. Apparently it's going to disappear. I'll put it back in a second. That leaves us with the 6, the 4, the 3, and the 5. 4 out of the total 6 outcomes of my die. And so what that means is the probability of not A from my Venn diagram are the outcomes that are not in A. 4 out of the 6, which when you simplify is 2/3. exactly the same as what we worked out with our rule. So I don't care which you choose to use. Some people find the Venn diagram quite useful. I find it more useful for certain questions. So like in the next question where it's asking, are the events mutually exclusive? For me to see it visually, so much easier. Obviously, if you can see it in your head, that's cool. But it depends on who you are as a learner. So sorry. Sneak attack. All right, so question D does say, are the events mutually exclusive? Now we've got 3 events here, so we're going to have to determine whether A and B are mutually exclusive, A and C, and B and C. Now this is why I'm saying a Venn diagram is so useful, because all I need to do now is look and see if there's an intersection between the two. Thank you, Emmanuel. I do apologize. He was just saying bless you. So A and B, ignore C. If we just look at A and B, so if we go to our little Venn diagram here, let's grab another color. And we look at the events A and B, we can clearly see that there is an intersection between the two. Because there is an intersection between the two, it means that they are not mutually exclusive. It doesn't say give a reason, but if you wanted to give a reason, it is because there is a common outcome. Or there is an intersection, whatever you wanted to do. If you wanted to prove it with your probability rule, you could do so, but all it's actually asked here, are they mutually exclusive? You would say, yes, they are, no, they aren't. That's what the question's asking us to do. Okay, so that's A and B. If we now go to A and C, so again, let's grab a color. A and C is now the yellow goldy circles here. There is no intersection. There's nothing overlapping between the two. So that means that they are mutually exclusive. And again, if you wanted to be fancy now with your probability terminology, you could say the probability of A and C is equal to 0. There is no intersection between the two events here. Right, the last one is B and C. So take a look at your Venn diagram or use whatever method you want to use. I'll give you 30 seconds and I want you to tell me if they are mutually exclusive. So you can just say yes, they are, or no, they aren't. B and C. Are they mutually exclusive? I want you to tell me. Nice, Emmanuel. Okay, so exactly as Emmanuel said there, guys, they are not mutually exclusive because if you look at B and C, so the blue circles, there is an intersection between the two of them of that value 4, so they're not mutually exclusive. And again, probability of A and B is not equal to 0. There is an intersection, there is a common outcome, whatever you wanted as a reason, if you had to give a reason. Right, so it's important for you to be able to identify whether or not events are mutually exclusive. Right, question A says determine the probability of A or C. So now I'm going to have to get rid of all of these fun doodles. When we are asking you for the probability of A or C, or we use the word or, what that means is I don't care if it's A, I don't care if it's C, I don't care if it's A and C, so I don't care if it's the intersection between the two. I just care that it's one of them. That's it. So A or C, we now need to, if you wanted to use your Venn diagram, you could. Or you can just use your probabilities. Again, it makes absolutely no difference. We now need to go and work out that probability. So I'm going to show you with the probability rule and with the Venn diagram, just so you can see. Once you have a Venn diagram, it does make it a lot easier to answer your probability questions, but that's if you choose to go and draw a Venn diagram. All right. So A or C, or I've taken off some of my outcomes. Yeah. A or C means outcome 1, outcome 2, and outcome 4. Those are all outcomes in one of the two of them. Don't really care if it's both, which it isn't. We know there isn't an intersection, but it's one of them. So there are 3 outcomes out of my total 6. So the probability of A or C is 3/6, which is a half. That's nice and easy if you use your Venn diagram. If you don't use your Venn diagram and you choose to rather use the probability rule, which many people do, probability rule says that the probability of A or C is equal to the probability of A plus the probability of C minus the probability of A and C. So the intersection between the two. Right, so the probability of A, we've already worked out, it's 1/3, plus the probability of C, which is 1/6. Again, we already worked that out, minus the intersection, which we've just determined is 0, because remember, they were mutually exclusive. Yes, the yellow. Right, you just type this into your calculator. There's no reason to be fancy. You can find an LCD if you want to, but again, type it into your calculator. 1/3 plus 1/6 gives us 1/2. Exactly the same answer. So Venn diagram, probability rule, whatever. Makes no difference. You're going to get the same answer, you do you. Like I say, the Venn diagram is only helpful if you actually draw it, because sometimes they don't ask you to draw a Venn diagram, but you can if it's going to help you. Otherwise, you just go to your probability rule and you substitute in your information. That's it. Right, so with that being said, I want you guys to try question F for me. So question F is asking you to work out the, sorry, I left off the P, the probability of A or B. I'll chuck in our P now. Probability of A or B. So give it a try and let's see what we come up with. Okay, do we need another minute? Give me a thumbs up if you're done, or a thumbs down if you need more time. Okay, I'm going to take the silence as we're done and not that we're not doing anything. Okay, so probability of A or B, again, you can use your Venn diagram if you want to. If you are going to use your Venn, I don't care if it's A, I don't care if it's B, I don't care if it's A and B, it just must be one of them. So that would be 1, 2, 6, and 4. So that's 4 outcomes out of the total possible 6 that we have. So using your Venn diagram, it would literally just be 4 over 6, which is 2/3. So again, if you have a Venn diagram, personally, I think it's a lot easier to work with a Venn diagram. That's just my personal preference. But if not, you go to your probability rule. So the probability of A or B, I'm not going to rewrite the whole rule, but is the probability of A, which we know is a third. Let's do this. Plus the probability of B, which we know is a half, minus the intersection between the two. Now remember, 4 was the intersection between B and C, which means that it's one of the 6 options. Don't know why I'm saying A and B. 2 was the intersection between A and B. So minus 1 out of 6. Again, type it into your calculator. There is absolutely no need for you to try and work out LCDs and do this in your head. There's no reason for that. Just calculator. A third plus a half minus a sixth does give you 2/3. So once again, exactly the same answer. Makes no difference. I think a Venn diagram is easier if you can draw one, but if you're struggling to draw one, just use the rule. The rule is there for a reason. It's for you to use. Right, question D says, are the events B and C independent? Now, for whatever reason, the last lesson my brain was not vibing with C or B. Just it wanted to do its own thing. So I'm going to do my best to understand the alphabet better in this lesson. If events are independent, remember what that means is that the probability of B and C would be equal to the probability of B times the probability of C. Now, when you are wanting to show that events are independent, prove whatever, you cannot work with this as an equation. So you cannot just substitute in as an equation and say, oh, okay, cool, well, the left equals the right, so we're sorted. Unfortunately, you're trying to prove that they are independent. If I said to you, events B and C are independent, determine the value or determine the probability of whatever, then cool. I've told you they're independent. You can work with it as an equation. But unfortunately, in this case, you're wanting to prove left equals right, essentially. So we've got the left-hand side and we've got the right-hand side. We want to prove that they're the same. So the left-hand side is the probability of B and C. So how you choose to do this, completely up to you. If you have the Venn diagram nice and easy, we can see that that is one outcome out of the total possible 6. So the probability of B and C is equal to 1 over 6. Perfect. On the right-hand side, we've got the probability of B times the probability of C. Now we know those two because we've worked them out. The probability of B was a half. The probability of C was a sixth. And if you multiply them together, you get 1 over 12. Now that's not the same. The left-hand side is not equal to the right-hand side. So we know that the probability of B and C is not equal to the product of those two events, probabilities. And because of the fact that they're not equal, we can therefore say they're not independent. Now, guys, please don't say they're dependent. That's not a thing. They either are independent or they are not independent. That's it. You've proven it because you've shown that the left isn't equal to the right. They're not independent. You're done. Okay, you don't now need to go and prove what they are. That's not what the question said. It just said, are they independent? We've proven that they're not. We're done. All right, so that's pretty much probability and the use of the rule and Venn diagrams on a basic level. We will do Venn diagrams a bit more in detail on Wednesday. In one example, we are going to do some more, but let's take a screenshot of this first one because there were a fair amount of questions. There were 7 covering a broad range. So let's screenshot that and then we'll have a look at example 2. Okay, so that's A to D. Right, and then E to G. Okay, now guys, the next few examples are very much more what you can expect in an assessment, where we give you a bunch of information about different probabilities, about the events, and then we ask you an unknown. Right, so example 2, bigger again. Example 2 says you've got two events, x and y, are such that the probability of x is 0,4, the probability of y is 0,3, and the probability of x or y is 0,6. Determine the probability of x and y. Now, what's really important for you to take note of here is that I haven't told you that they're independent. I haven't told you that they're mutually exclusive. I just said you've got two events. So we go back to our probability rule. Probability of x or y is equal to the probability of x plus the probability of y minus the probability of x and y. Now, again, this is not something you need to learn off by heart, okay? It's on your formula sheet. There is no reason for you to try and learn it off by heart. It's there for you. That's it. I'm just going to keep writing it down so that it sticks in our heads. Right. Formula sheet, don't need to know it off by heart. So what we've been asked to find is the probability of x and y. So I'm actually asking you for this last term here. If you want to go and manipulate this formula first to isolate probability x and y, fine. But otherwise just substitute in and solve for them, which is what I'm going to do. So the probability of x or y, we were given as 0,6. So 0,6 is equal to the probability of x, 0,4, plus the probability of y, 0,3, minus the probability of x and y. So that's what we're solving for. Inverse operation says I'm going to subtract 0,4 and 0,3 on both sides. So that leaves me with 0,6 minus 0,4 minus 0,3, which is negative 0,1, is equal to negative probability x and y. Now, obviously, we don't want negatives, so we just sort that out quickly. And we get that the probability of x and y is equal to 0,1. That's it. Done. Substitute into your formula. You're good as gold. And that's why the formula is so useful. Here we didn't have a Venn diagram. We didn't have a diagram. We didn't have a tree, nothing. But we've got the formula. Substitute in, solve for what you need to solve for. Right, so if you want to take a screenshot of that quickly, and then we'll move on to the next example. Now, the next example, I do give you a bit of information that is useful to you. Now, again, how you choose to use that information is up to you. I'll tell you what I mean by that in a second. But when we start to tell you something about the events, they are independent, they are mutually exclusive. You can now use that in your working out. So example 3, I've said two mutually exclusive events, A and B, are such that, the probability of A is 0,3 and the probability of not B is 0,4. Determine the probability of A or B. Cool. First things first, I'm telling you that these events are mutually exclusive. So I'm telling you that the probability of A and B is equal to 0. Mutually exclusive, there is no intersection between your events. The next thing that you need to bear in mind I've given you is the probability of not B. If you want to use your probability rule, you need the probability of B. So we know that the probability of B is found by saying 1 minus the probability of not B. I'm just going to use the apostrophe. And so that would be 1 minus 0,4, which is 0,6. So now we've got that information. We have been asked to determine the probability of A or B. So if you go back to this rule, we want the probability of A or B. Like I said, I'm just going to keep writing this rule down so that it becomes part of your dreams, basically. Probability. Okay, whatever. Okay, apparently not whatever. Who knows why? So the probability of A or B is going to be found by us saying the probability of A plus the probability of B. Now I'm not, or you can add minus the probability of A and B if you want to. But remember, because they're mutually exclusive, we know that that's 0. So we're just subtracting 0. If you want to fill that in, that's absolutely fine. And that's why the rule is so nice to use, is because you know it's mutually exclusive. So you're just substituting 0 there. If you know it's mutually exclusive, then you know you're just adding the two probabilities, whatever you are more comfortable with. Okay, so in doing that, we know that the probability of A is 0,3, and we've worked out the probability of B to be 0,6. You can stop there because, again, you know they're mutually exclusive. You know there's no point of intersection or no intersection between events. But if you want to say -0, there's no harm. It's not going to do anything. But we have now worked out that the probability of A or B is equal to 0,9. All because we were told they're mutually exclusive. We know that means there's no overlap or no intersection between your events. So all you're actually doing is adding the probabilities of the two events together. So when we give you information about your events, you can use that in your working out. All right, let's do this one and then we'll take a screenshot. Two exhaustive events. So again, I'm giving you information here. Okay, so when events are exhaustive, remember what that means is that the probability of A or B occurring, and let's maybe use the letters we have here. So let's go X and Y, is equal to 1. Everything, oh, guys, X or Y, everything falls into one of those two events. So you've got 100% probability of getting either X or Y. Are such that X is equal to 0,9 and the probability of X and Y is equal to 0,7. Determine the probability of Y. Now remember, exhaustive events still have an intersection. It's complementary events that do not have an intersection because they are both mutually exclusive and exhaustive. So again, we just use our probability rule. But what we know is that the probability of X or Y is equal to 1 because it's exhaustive. Again, we're just going to write down our rules so that it stays with you forever. So the probability of X or Y is equal to the probability of X plus the probability of Y minus the probability of X and Y. We have all the information that we need. We're going to go solve. According to the question, it said determine the probability of Y. So we're looking for that second term on the right-hand side. Now we substitute in. Probability of X or Y, it's exhaustive, so it's 1 is equal to probability of X, which is 0,9, plus the probability of Y, which is what we're trying to find, minus the point of intersection, 0,7. Use your inverse operations. You go and add and subtract what you need to add and subtract. So we would subtract 0,9, but we would add 0,7 because inverse operations to get the probability of Y. 1 minus 0,9 is 0,1 plus 0,7 is 0,8 is your probability of Y. And that's it. So when I actually give you information about your events, you can use that to go and answer questions. However, like in the last question of example 1, if I'm asking you to prove that they're mutually exclusive or independent or whatever, you actually need to work with the two sides of your equation separately and prove that left is equal to right. Okay, so take a screenshot of those two, and then I'm going to put up an example that you guys are going to try by yourselves. Maybe if you've got questions, just ask. Okay. Right, so there's 3 questions here. Have a go. 3 questions, let's say 5 minutes. You shouldn't need more than that, but I'll give you 5 minutes and then we'll see where you're at. And remember, if you're not feeling too sure, just ask. Righty, let's have a look. Does anyone need some more time, or can I show the answers? Just let me know. Right, I'm gonna assume we're fine. Let's have a see. Okay, let's make this a bit bigger. Right, so A, you were just given events. You were told C, C and D, and C or D. So I just wanted the probability of D. You sub it into your rule and you solve for what you want. B, I told you they're mutually exclusive. So that means that the intersection is 0. So that means when you say minus the probability of A and B, it's 0. And then question C, I told you that they are independent. So what that means is that the probability of A and B is equal to the probability of A times B. So you can work with the information that you have and knowing that they're independent in order to get the probabilities that you wanted. So what I mean by that is, because it's asking you for the probability of A or B, I just grab my highlighter. Oh, that's chunky. Right, probability of A or B. According to your probability rule, you need to know what the probability of A is, what the probability of B is, and what the probability of A and B is. You were given A, and you were given not B. So not B is nice and easy. You just say 1 minus that, and you get your probability of B. However, to get the probability of A and B, you need to use the fact that they are independent. So remember our independent rule, let's get another color here. Independent says that the probability of A and B is equal to the product of each of your probabilities. So that's why, of course, it's gonna cover it. So that's why over here, I just multiplied the two together because that's what my independent rule says. So I'm actually just gonna write that here. So the rule for independent events is the probability of A and B is equal to the probability of A times the probability of B. And that's what I'm doing over here. Because I needed to go and work out what the probability of A and B was so that I could substitute into my formula. So C was a little trickier. But again, because I'm telling you that they're independent, you clearly have to use that. So remember, guys, we don't give you useless information. If I'm saying it's independent, you're going to have to use that. If I'm giving you probability of not B, you're going to have to go and probably find the probability of B. So whenever we give you information, it's because we want you to use it. So like I say, C a little trickier, but hopefully nothing too onerous. So I'll leave that there for you guys to take a screenshot of. Right, and then I'm going to end off there. I know it's 2 minutes, but I don't think I'll get through another example in 2 minutes, which is not the end of the world. On Wednesday, we will have a look at Venns, tree diagrams, and contingency tables. We will then obviously have our holiday for a little bit, for 2 weeks. And then back finishing off counting principle, which is a grade 12 probability, and then straight into calculus. Like I said, Wednesday, don't forget, we're going to use the Google Meet function. This will all be sent to your parents and guardians in case you forget, and I will put it on the classroom. For those of you still finishing exams, best of luck. For those of you finished exams, well done, you did it.